the name of Allah, most beneficent, most merciful. First of all, I'm thankful to the organizers for inviting me for this talk. The topic of my talk is RF principles, transmission line, and RF components. Basically, I want to start from very initial theory, which is developed around waveguide components, transmission line, and related RF theory. So I belong to Pakistan Institute of Nuclear Sciences and Technology, which is an establishment of Atomic Energy Commission. Few introduction to my project, few slides. Here is a institute, and in that institute we have a LINIC project. What we have done so far, we have developed electron beams, simulation, transport, and their diagnostic. We have designed few accelerators, integrated them, commissioned them, and operated them as well. We also have developed few RF components for transmission assembly, and we have designed our accelerator control and electronics related to these accelerators. We also have designed accelerator shielding, collimation, and Phoenix the dosimetry of these accelerators. What sort of facility we have? We have a accelerator design and operation setup, electron gun design and development operations lab, magnet design and test and calibration lab, modulator which runs these RF sources, waveguide design and development lab, control electronics lab, and accelerator bunker and control room lab. So this slide shows basic ingredients of a accelerator, and legend tells us that these components we have locally developed, and these components which are little darker color here are partially developed by us, and we are lagging a lot behind in these items, especially RF amplifier and vacuum components. Now come to the talk. Outlines of talk are as follows. I have divided this talk into two parts. In first part, I shall discuss a few topics from this outline: RF power transport basics, transmission assembly components. These are waveguides, RF loads, circulators, isolators, pulse compressor. Why pulse compressor is used? Sometimes we have low power devices or amplifiers, and we want high power pulse. So some waveguides can be designed to compress that pulse. The magnitude with which it is compressed, its amplitude is increased by the same factor. Then we shall talk about RF power measurements. We're using directional coupler, frequency tuning, separating power for more than one RF cavities, or we can couple power from waveguide to the cavities. And very important topic, RF window. So we have RF source, then we have a RF transmission line, and this RF is transmitted to a device under test, and in between there are RF windows. Whenever we talk about RF source, it is a vacuum device, and from vacuum to any transmission line, you need isolation, which can isolate vacuum and transmission assembly. Similarly, when this RF is transmitted to any device, for example, accelerator, we again need a waveguide assembly. RF window. And for RF window, we need a low loss, low refraction, high reliability, and efficient power transfer to the duct. What are the transmission line assemblies? There are three types of transmission line assemblies that can be two wired lines, often used for indoor antennas for very low power. Low power. It can be for radio or TV, and the problem with them is that they radiate to the environment, cannot be used for high power transmission, and they can't carry the high power. The second is strip line transmission assemblies, often used for microwave integrated circuits, and their capability is also very low. Now, we can use coaxial lines to transmit RF from RF source to the device under test. Often used for power transmission and connection of RF components, high loss above a certain frequency. These are frequency dependent. If you go into the higher frequency regime, the losses are increased significantly. So for high powers, coaxial cables cannot be used to transfer the power efficiently. The most important for high power transmission is waveguide assembly, which can be rectangular, cylindrical, or elliptical. So before going to discuss waveguide assembly, we have to consider the skin depth effect. The skin defect effect is defined by this equation. Here, rho is resistivity of the conductor. For efficient transmission of power, we need very low resistance material for the waveguides. Similarly, the frequency define the skin depth. As we increase the frequency, the skin depth decreases. And for 3 gigahertz, this skin depth is very small. It's almost 1.2 microns, which mean a small discontinuities or roughness on the surface of the waveguides or waveguide assembly can cause ohmic losses and heating. Here is a table which is telling about the parameters of different materials, their resistivity, and their skin depth at 2 megahertz. The best one is silver here. And mostly copper is used. And sometimes copper is coated by this silver. And this layer may be 5 to 10 micron, because for high frequencies, skin depth is very small. And if you are in 3 gigahertz, 1.2 micron is the skin depth. Now, how the microwaves or electromagnetic waves are produced? Consider a current carrying conductor as shown here. Current is moving upward. If you use the right hand rule, your thumb is along the direction of current, then your fingers will tell us, will indicate the direction of magnetic field around it. Now, if this current is changing and it's changing its polarity as well, the magnetic field around the conductor will also change. And you know, every magnetic field which is changing produce electric field around it, and every electric field which is changing produce magnetic field around it. And this way, a series of electric and magnetic fields are produced. And if our conductor is stationary, then linearly polarized radiations are emitted, and electric and magnetic fields are perpendicular to the direction of propagation, and these perpendicular these waves are called transverse electromagnetic waves. And if somehow our conductor is moving, these polarization may change from linear to circular or elliptical, depending upon the motion of the conductor. Now, in the free space, these fields are moving in some way that the electric and magnetic field are always perpendicular to the direction of propagation, whether they are linearly polarized or circularly polarized. But when we apply some boundary conditions, for example, we talk about rectangular waveguides, then one of the component, whether it's electric or magnetic, is along the direction of propagation. And this is due to the solution of our wave equation. When we solve this wave equation applying boundary conditions, like here, we have a rectangular waveguide. Its one side is a centimeter long and other side is b centimeter high. So applying these boundary condition, we get the solution of this wave equation, which can be defined by this equation. And there is another particular effect on propagation, that there is a cutoff frequency, which can be defined by these parameters, which are A and B. And here M and N, which defines the modes, will be discussed shortly after this. So these modes inside these rectangular waveguides are distributed. That TE10 mode is at the lowest frequency. TE20 mode is double than that frequency. Actually, it's these are scaled by cutoff frequency of TE10 mode. Now, when RF follow through or passes through these waveguides, we have transverse electric mode or transverse magnetic mode. Here, this side, we have transverse magnetic mode. As I earlier explained, these transverse magnetic modes are modes in which electric field is along the direction of propagation, but magnetic field is perpendicular to the direction of propagation. Similarly, in TE modes, electric field is perpendicular to the direction of propagation, and magnetic field is along the direction of propagation. So generally, the waveguides are such a way that the longer side is double of the shorter side. If we apply this condition to our previous equation, where I have shown you the cutoff frequency, and I'm not calculating here the formula for cutoff frequency, instead I'm calculating wavelength, cutoff wavelength for these modes. Then it is simplified to this formula. Now, as we have seen, TE mode, cutoff wavelength, can be defined by the longer side. It is double of the longer side. If it is 10 centimeter, then wavelength of cutoff frequency will be 20 centimeter. Similarly, for cutoff frequency, a wavelength of cutoff frequency of 0 to mode will be half of the wavelength, and so on other frequencies. All these modes lie between A and 2A. Similarly, we can drive transverse magnetic modes, their cutoff wavelengths, and using same that assumption that our longer side is double than the shorter side, and all the modes transverse magnetic mode also lie within this limit. Their wavelength is from A to 2A. Moreover, the transverse electric mode, which is 1-0 mode, is most efficiently propagated in these waveguides. Now, how these modes are defined? This TE10 mode means the electric field intensity maxima along longer side is 1. There is 1 electric field intensity maximum when RF is passing through this waveguide. And when we say TE20 mode, it means that there are 2 electric field maximums along the longer side. And if we talk about TE01 mode, then there is 1 intensity maximum along the shorter side. But if we talk about TE11 mode, then we have 1 electric intensity maximum along the longer side and 1 intensity maximum along the shorter side. Similarly, for TE21 mode, we have 2 intensity maximas along longer side and 1 intensity maximum along the shorter side. Now, when a traveling wave is passing through versus standing wave, the maximum electrical field strength in the standing wave is double than the strength of the traveling wave. Hence, when there is a traveling wave in an accelerating structure, the power is 4 times higher than when there is a standing wave in the waveguide, the power is 4 times higher than the case for same frequency and same power of traveling wave field. Now, some few properties of transverse electric mode 1-0, because it is more efficient mode to propagate RF through the waveguides. Its cutoff frequency is defined by C by 2A. And its cutoff wavelength, we have already discussed, it is equivalent to 2A. And there is another effect when we have electromagnetic waves bounded by boundary conditions. Their wavelength is increased. That wavelength is called guide wavelength. And it is always larger than their wavelength in free space. And this guide wavelength can be defined by lambda divided by 1 minus lambda by lambda cutoff square root and whole square root. Similarly, the propagation constant is defined now. This beta g propagation constant inside the waveguide depends upon the lambda, because we have a fixed waveguide. Its A is fixed, its B is fixed. Only the frequency is changing. So we say we can see that if we increase the frequency which is passing through the waveguide, the propagation constant decreases, and the frequency, wavelength of TE10 mode is maximum in this case. So its propagation constant is maximum. So most efficient mode to transfer energy to the waveguides is TE10. There are some standard waveguides. They have frequency ranges. Their frequency, cutoff frequency for TE10 mode is also given in this table. For example, if we talk about WR284 waveguide here, then its A is almost 2.84 inches and shorter side is 1.34 inches, and its cutoff frequency is 2.08, and its range is 2.6 to 3.95 gigahertz. Now, if we talk about the power carrying capability of these waveguides, it can be defined as peak power that a waveguide can carry is given by E maxima, the maximum electric field produced or formed inside the waveguide. It's also involved with its wavelength as well. But this Emax depends upon whether it is a traveling wave or standing wave. If it is a traveling wave, then Emax will be 4 times, higher than 2 times higher than the traveling.
Sorry, why waveguide? Wave go through the video. Why need the waveguide?
Why we use the waveguide?
Yes, yeah.
To direct the RF power to the particular device in throwing this RF power into the free space, how we can inject it to accelerating structure or any RF device.
Was it maybe lost its energy or something?
I think all of the RF power will be wasted into the free space. You have to direct it to a particular point where you want to use it. You want to accelerate the electrons. You need an accelerator with RF fields inside it. Maximum the field gradient in the accelerating structure is higher the power you can gain.
The optimum is a rectangular with size of.
Yeah, it depends upon the frequency. I have given you the range, different waveguides. For example, if you have a WR2300, then it suffices for 320 to almost 490 megahertz. But if you are working in a S band, then you use WR284. Then the attenuation of these rectangular waveguides can be calculated by this formula. It is directly proportional to A naught, which is 310 to which is 10 to 7 dB per meter for copper. It is attenuation of RF per meter, actually. A is width of the waveguide in meters, B is height of the waveguide in meters, and lambda is the wavelength in the free space. And if you have a rectangular waveguide with half shorter side is half of the longer side, then this formula can be further simplified. Here in this graph, it is shown that what is the peak power carrying capacities of different waveguides. Now, looking to the circular waveguides. Previously, we discussed about the rectangular waveguides. If we come to the circular waveguide, to solve these wave equation for these circular waveguides, we write wave equation in cylindrical coordinates and use the pressure of variable method And these three independent equations are obtained. And when we apply these boundary conditions, given that the radius of this cylinder is A, and here I have used the second additional condition, length of the cylinder. Previously, I used the two boundary conditions along the. I can show you along X and Y. Length was unlimited because these waveguides are used to transfer power from RF source to end node, where you are injecting this power to the accelerating structure or some other device under test. But in cylindrical cavities, these cavities are mostly used to accelerate the particles. So I have used three boundary conditions. And here we have three subscripts N, M, and L. Again, this defines the modes which can be propagated through these cylindrical waveguides, or which can be resonated these cylindrical cavities. Here, the solution of these equations give us E field inside these waveguides. In these equations, there is a Bessel function, and it's governed by these PNM, radius, and A. These P subscript and NM are roots of the Bessel function. A is a radius, and R is a running parameter. So the roots of Bessel functions are given. Consider that you are exciting E0, 1, 0 modes inside this cavity. Then in that case, the first 0 of the Bessel function is lying here, and it is 2.450. It will define the radius of the cylindrical cavity. And if you select the radius in such a way that by selecting first 0 of Bessel function, then you will be able to excite TM010 mode inside the cavity. It means if we look the cavity cross-sectional area, you will get maximum electric field inside the center in the center of the cavity or waveguide, and this electric field will be minimum near the walls of the cylindrical cavity, and magnetic field will be vice versa. Here it is TM010 mode, TM mode. So electric field is along the direction of propagation, and magnetic field is along the transverse direction of the propagation. So here we have shown that the electric field is along the propagation, and magnetic field is along the walls. It is maximum near the walls and minimum at the center. Now, if you want to excite TM020 mode, in that case, we have two intensity maximas, electric field intensity maximas. One will be lying at the center. Now you have selected the radius in this way. This is the radius 5. This value is you have selected this value 5.52, and A is constant. R is a running parameter here, and you will get a field inside the cavity which is such a way that there is one intensity maximum at the center, and other intensity maxima will be lying in between here. Here, Bessel function, zeroth order Bessel function is maximum at the center. It is minimum at this point, which is first zero of the Bessel function. Then there is another intensity maximum, which is at this point. And it is again minimum at the, or zero at the walls of the cylindrical cavity or waveguide. Now, how we can couple this RF to the devices? There are three schemes. Actually, there are two ways to couple RF. One is called magnetic coupling and other is called electric coupling. In magnetic coupling, you first of all we can couple it through the coaxial cable, and then we can also couple it by the waveguide. For low power, we use coaxial cables because it is cheaper, its handling is easy. But for high power, we use waveguides. Now, there are two types of couplings. One is electric coupling, other is magnetic coupling. In electric coupling, if you are using a coaxial cable or antenna, then we insert antenna at a point where electric field is maximum. For example, if we have a pillbox type cavity, we can insert antenna here, but here we have to accelerate the electron beam. It will disturb the field. We can place this electric antenna here at this point, and it will properly couple the electric field to the cavity. Similarly, there is a way to couple RF through the waveguides. That can be magnetic coupling or electric coupling. Here we have waveguide, and then we have a cylindrical cavity, and we want to couple RF field to this cavity. In this case, we can have a magnetic coupling or we can have electric coupling. If we are exciting TM010 mode inside the cavity, and in that case, magnetic field is maximum near the walls, and we use this scheme because electric field is maximum, magnetic field is maximum near the wall, and we couple it at the place where magnetic field in the rectangular waveguide is maximum. Now, when we couple RF to from waveguide to the cavity, for example, we have a cavity which has been excited by TM010 mode. Electric field is maximum at the center, and magnetic field is maximum at the walls of the cavity, and we couple it through the waveguide. Of course, this coupling hole on one side can generate a perturbation. This perturbation disturbs the field, and this field is skewed on one side. When electron beam, which is going to be accelerated by this field, passes through this cavity, it is also deflected on one side, and our beam doesn't remain aligned with the rest of the structure, and we can't get the proper acceleration and proper hitting of the beam on the target. So we can eliminate this screen by changing the dimension of that coupling cavity. There are two ways. One is we can produce same perturbation or coupling on the opposite side. but we don't couple RF from that side. We couple RF from this upper side. This is slightly mitigated the problem. But again, you can see instead of circular field lines of magnetic field, these lines are almost elliptical. To cater these elliptical lines, we have, instead of a circular cavity, we have a slightly elliptic cavity. When cavity, there is no RF coupled to the cavity, these are elliptical fields, almost not circular, but when RF is coupled, they are perfectly circular magnetic field lines all over the cavity. Here we have shown how these compensating slots are defined, and secondly, we can also couple RF field from two slots, but there is need to be very careful that a phase difference between two slots can cancel the field inside the cavity. Now, when we measure the S parameters, especially S11 parameters, we can guess what sort of coupling we have provided. We have done so far. Coupling can be three types. One is undercoupled. The second is critical coupled, and the third one is overcoupled. These are three, because blue is showing undercoupled, green is showing critical coupled, and red is showing overcoupled. What are their disadvantages? Generally, when we are coupling RF to an accelerating structure, especially when this accelerating structure is a standing wave structure, we use almost undercoupled scheme. Because when our beam is loaded, this coupling becomes critical. But if we have a critical coupling and beam loading effect increase the coupling as well, and a slight change in the frequency can be very significant, can cause very significant changes into the power gained by the beam. Because slightly change in the frequency will shift these coupling curves right or left, and beam seeing this power will be find a huge difference. Here, if it is coupling, RF power is in megawatt and a slightly change occurred, then this coupling can goes to into the 80 to 85% of that part, and beam quality is decreased.
Is it also possible to use like impedance matching stubs? Instead of
yes. Whenever we define, when we design, we use impedance. But when frequency is changed, there is cavity is not resonant to the frequency, and RF power is changed inside the structure, accelerating structure, and that change in RF also change your beam quality, which is being accelerated by this RF field. Here, again, it is shown where you couple your cavity to get maximum coupling. For example, if we couple our cavity here where the electric field is maximum here, no RF power will be coupled because outer wall of the cavity has maximum of magnetic field. But if you couple here where there is a magnetic field maxima in the waveguide, the cavity will be coupled to the gate. And you can also use loop antenna, and that direction of loop antenna is also very important. You can change your coupling by rotating this loop antenna. For example, if it is your cavity is like this and your loop is in this direction, minimum coupling will occur. But if you rotate your antenna and loop is in this direction, maximum magnetic field lines, in this direction, maximum magnetic field lines will pass through the antenna and RF will be coupled, but in this direction, very minor magnetic field lines will pass through the antenna and less RF will be coupled. So, summary of coaxial and waveguide couplers. Waveguides have large dimensions, and coaxial couplers or coaxial cables have smaller directions. And these are coaxial couplers or coaxial cables are efficient at low frequency, and they are preferred at low frequency. For high frequency, we need always waveguide assembly and couplings. The power handling of waveguides is much higher than coaxial cables. For higher power cases, we use waveguides, and attenuation is much lower in waveguide components, waveguide assembly, while it is very high for high frequency coaxial cables and couplers. The vacuum pumping is better for waveguide components. Generally, when you pass RF through the waveguide components, in here, for example, if I talk about WR284, which is for the S band, the power capability of this waveguide in here is less than 1 megawatt. To increase its power capability, it is filled with SF6 or any inert gas, which mitigate the arcing inside the waveguides. But if it is a vacuumed system, waveguides are vacuumed, its power carrying capacity is increased many times. Okay, well, the next is how if we need to vary the coupling, which one is better? Because you can't vary the coupling in waveguides once it is fabricated, whatsoever or what type of coupling you have done. If you are both very lucky, will be achieved after fabrication and brazing. But if you have coaxial cable, you can tune your coupling by tuning the direction of your antenna. Because this antenna is flanged with the cavity, and you can open the flange, you can change its direction this way to optimize your coupling. Moreover, you can easily cool the waveguide components, but it is very hard to cool the coaxial coupling and coaxial waveguides, coaxial transmission assembly. Now, how we can distribute RF to more than one RF source, RF devices. Suppose we have 3 or 4 accelerating structures, and we want to couple them from a single RF source. This way, we have 2 type of components. One is called 50-50 beam splitter, and other is called shunt T. I shall discuss the shunt T. 50-50 beam splitter is quite simple as compared to the shunt T, because it is a waveguide which is divided into 2 ports. It's a 3-port waveguide. RF from one port is divided into 3 ports. But Shanti is a little different. I shall explain in the next slides. So this distribution of RF power can be any sort of distribution. It can be tree-like, it can be linear. And one thing is important to note that if you are distributing your RF, you need a circulator at the entry of every RF source. This circulator mitigates any unwanted reflection back of RF from that insulating structure to the RF source or to the other accelerating structures. We shall then discuss this circulator as well in the next slides, how it works. So before designing to this distribution, we consider how many devices we want to feed with this and what sort of distribution we should have, what sort of resources we have, because for every source you need one directional coupler, one circulator dump the RF which is reflected back from the accelerating structure, and directional coupler measure the power which is injected to the your accelerating structure and the reflected back part. It has dual ports. It's called dual directional coupler because the power going inside is measured, the power is reflected back from the cavity is measured. That's why it's called dual
In
directional.
the linear distribution case, how do you adjust the coupling ratio to make sure the
I shall discuss. This is called Shanti, which adjusts the ratio. I shall discuss this Shanti in coming slides. Here is about a coaxial line. Its characteristic impedance is defined by this formula. D is the inner dimension of outer radius, and small d is outer dimension of inner radius. So by changing d's here, we can tune the characteristic impedance of these cables. And here these parameters are discussed in this table. Here formula define the power carrying capacities of these coaxial lines. So we peak max which can be carried by these wires is defined by these d's, their ratio, and small d. If you want to increase the peak carrying capacity, you must increase the small d and their ratio as well. Here is a graph for different cables. Their maximum power carrying capabilities is shown in this graph. Now, similarly, the attenuation of these coaxial cable is defined by this formula. Here, characteristic impedance is very important. Frequency is very important because this attenuation is directly proportional to the square root of RF frequency. And if there is a dielectric in between these two conductors, where one is defined by inner dia and the other is defined by outer dia, smaller conductor by small d and larger conductor by large d, then here is the parameter which defines their presence. Now, when RF power is coupled to the device, there is always a reflection. Some power is reflected back to the source. That reflected power is dumped to some sort of load, because if it is not dumped to the load, it goes back to the your RF source, and its efficiency and its stability is compromised. And that reflection coefficient is defined by this equation. Here VR is reflected power and VF is forward power. Sorry. Now you can measure the Vmax inside the your transmission line, not by the power your source is generating, but the power is reflected back from the your that device under test, because this reflected power form standing wave, and the power inside the transmission line is increased. If all the power is reflected back, then the power inside the transmission line will be 4 times when there is no reflection. So voltage standing wave ratio is defined by Vmax divided by V minimum, where Vmax and V minimums are defined. And if you talk about reflection coefficient, then these are defined by this formula. Now I come to the point. All these power is distributed. This waveguide component is called high power shunt T. Now this shunt T we designed at our project is used WR284 waveguide. There are 3 ports. RF is coming from this port and passing to this port. Now, if our plunger, which is here at this point, where arrow is showing that corner, then all the power coming from this side to this side passes through the waveguide and goes to the dump or accelerating structure where you wish to use it. But if this shunt is pulled back, the power fraction of power is reflected back, and that fraction depends where your plunger is. If it is at lambda g by 2, again here I'm talking about the waveguide of frequency you are talking about inside this particular waveguide length of the wave you are talking about depends upon its waveguide. This if it is pulled back lambda g by 2, then all the power is reflected back, because this cavity or shunt behave as a short. But if it's again placed here, then it acts as an open source. This plunger can be operated at runtime by any stepper motor, because a slightly moving forward or moving back can define how much RF you want to inject to the your accelerating structure. Here we have integrated into 6 MeV transmission line assembly. You can see this is this high power shunt T. Inside this there is a plunger, and this is motor which drive this plunger. And these are end minimum points. One is here, one is here. When our plunger is here, the power injected to this side is zero because it behaves as a short, and all the power coming to this direction is reflected back. And when it is here, all the power passes through this waveguide and goes to the accelerating structure or any dump or any that device under test. But there is something special about this frequency or separator, that when we have our plunger at this position and slightly move upward, the power is linearly changed. But when we reach this point, it is exponentially changing. A minor change in the plunger position can enhance very much RF power. So its behavior is like exponential, or like to say power law behavior. But if you have a dual directional coupler coupled to the your accelerating structure, you can find how much power is coupled and how much power is reflected back. Now, when we are measuring the power coupled to an accelerated structure, the power coupled and power reflected, power injected and power reflected difference define the power injected into the accelerating structure. There is another phenomena, because every cavity is not a perfect cavity. It can be perfect in your simulation or somewhere your imagination, but whenever RF passes through that cavity, current passes on the inner surface of the cavity, and ohmic losses are always there. And those ohmic losses produces heat, and some of power is dissipated in the form of heat. And if you want to measure that power, you have to play with your cooling channel. You must know what is the temperature of water coming in, and what is the temperature of water coming out, what is the heat capacity of water, and how much volume of water passes through this cooling channel every second. And you can handsomely estimate the power delivered to the electron beam or particles being accelerated. Here is a directional coupler which measure the RF power. Again, it is designed and measured. Cold test was conducted and integrated to our 6N linear structure. Actually, what is principle behind it? We have a small loop antenna here. You can see here a coaxial coupling port. But here you want to measure how much power is coupled to the system. You need very small coupling. You must know what is the coupling of your antenna. Efficiency is not required here, because here we are not coupling RF power to the structure. We are just testing how much power is coupling. For example, if you have a big bowl of rice and you can test 2 or 3 rice, you can test the taste. But in this case, you have a antenna which can be raised and lowered, and there is a slot inside the waveguide that can be circular slot or can be rectangular slot. A minor RF power is leaked to the antenna and it is coupled, and we know it is coupling. What is the coupling? If it is 50 dB, it means if there are you say 10 raised power 5 volt per meter gradient inside your waveguide, electric field gradient inside your waveguide. Your intensity of your electric field, if you mention in volts per meter, is 10 raised power 5, then only 1 volt will be coupled to the antenna. And this coupling you measure on your oscilloscope or on your power meter allow you to back calculate how much power is going in. Now one port measure the forward power and other port measure the reflected power. So the trick here is how we can adjust the positions of these two slots, that one only measure forward power and one only measure reflected power. Then we have to again know the waveguide length of that particular RF which are we passing through the waveguide. For example, if we are talking about 3 gigahertz, its wavelength in free space is almost 100 centimeter, but inside the waveguide, its wavelength becomes 139 point something, roughly you say 140 mm or 14 centimeter. Now, if these slots are perfectly placed at lambda g by 4, or integer multiple of lambda g by 4, if RF is coming from this side, it will be seen by this, always seen by this. Its coupling to the RF will be 10 raised power 60 dB or 50 dB, but the coupling of this port will be 80 or 90 dB. Means if there is a gradient electric field inside the cavity is 1 million volt, and your coupling of this antenna is 60 dB, it will read only 1 volt per meter voltage, and the signal you measure at your power meter or your oscilloscope will tell you how much power is passing or going forward. Definitely you have to include attenuation of your cable you're using, attenuation of any other attenuator to decrease the level of this signal you require must be added, and you will back calculate, and forward power is calculated. But when RF is passing through this waveguide in this direction, and if this is exactly at multiples of lambda g by 2 spaced, these two slots are spaced in this way that their spacing is lambda g by 2 or their integer multiple, then their antennas are almost identical, their position is identical, then their coupling will be 2 to 3 orders different. Its coupling is 60 dB, its coupling seen by wave will be 80 or 90 dB. Let's see, 160 dB, it gives 1 volt signal, and when it is 90 dB, it will give us 0.001 volt signal. So only RF power going forward is measured. But when the same RF power or some part of RF power is reflected back, now the power or field seen by this coupling becomes 60 dB for this port and 90 dB for this port, the next port. So only this port can read the reflected RF power, and this can't read this one. Its reading given by this port is 3 orders smaller. So the difference between these two readings, whether it's going forward or going reflected back, is called directivity. So you have to manage that directivity, maximum directivity. If you have 50 dB coupling of your first antenna and you designed it extremely well, and its directivity is 40 dB, then it is a very, very good good reduction coupler, and very efficiently you can measure the power. Now, the next thing is, when RF power is reflected back, you have to dump it somewhere else. You don't allow it to go to the your amplifier or RF producing devices, because reflected power, it goes to the that amplifier, it disturbs its stability. So these devices or these waveguide components which dump RF power are called water loads or dry loads, depending on what sort of material is used. Here we have designed a dry load, which is used for very high power dry load. As we are working on S-band parameter with the frequency of almost 3 gigahertz, it's 2.998 gigahertz. So we are working with the S-band waveguides. They are called WR284. Here the 284 number tells the longer side of the waveguide is 2.84 inches. So you can guess what would be the shorter side. If someone asks you to find the cutoff frequency of a waveguide, it's one longer side is 3 inches, or you say 100 mm, you can easily calculate, because you have to consider that other side is half of this one. This is the formula, and that's all.
How does water channel affect, the performance of the waveguide? Water channel, other than cooling, how does it affect?
This is isolated from waveguides.
Yes, because you said dry load simulations, the simulation result, how would it change if you had the water channel?
Yeah, but if you are using very high power, so you can use. Actually, water loads are of two types. Again, this is the most different case. We have water inside the waveguide. From one side, water is coming into the waveguide. From other side, it's going to the.
If it is inside the permittivity check.
Yeah, but you need then RF window to isolate this water from the rest of the transmission assembly. But here in this case, you don't need this RF window, because brazing of this RF window is a difficult and tough task. So that's why it is called dry load. If very high power, we need to cool from external walls. So silicon carbide posts, which are cylindrical type, are designed and integrated inside it. But again, when these posts are come into play inside the waveguide, the impedance of waveguide is changed. Now it is not exactly WR284 waveguide. You have to change the dimensions of WR285 waveguide to match the impedance with the rest of the transmission assembly. So here are the dimensions of this waveguide: shorter side, wider side, its length, radius of carbide post is given. Total ports are 26. Initial height of the carbide port is 12 mm, and the spacing between all these carbide posts is 42. Now these are quick results. When RF is injected or dumped, actually, we should use the word dumped. We are not inject power to these dumps. This is the power which is reflected back, and we have to dump it. Then the E field in the top figure shows that E field is slowly absorbed. Power is slowly absorbing, and then it is almost zero. And if somehow it is reflected back, it is again absorbed. Similarly, magnetic field is shown, and in the lower figure, the power is shown. But here, so here we have shown scattering parameters. These scattering parameters, which are called S11, here I have plotted S11 parameters, tells us that how much power is absorbed in the cavity. If this is the resonant cavity, the scattering parameter will be very, very small. Here it is given in dBs. And if it is not resonant, as this case, this will be little higher than that. The problem with this design is that fabrication of silicon carbide is very difficult, and it's required 2100 degrees Celsius temperature for sintering these carbides. Its machining is an issue. Actually, you have to have mold them into the 26 posts of different sizes. And the third issue is here, as we don't need efficient transfer of power through the waveguide, we can use a steel waveguide, which is easy to weld. In case of copper, we need to braze it. So here we have to also weld these silicon carbides posts, which is also a difficult task. Next is how much time?
No.
Okay, okay. I think I can discuss circulator. Okay. So circulator is a device which can allow RF to pass in one direction. When this RF is reflected back, that can't go back to the same direction. The magnetic field is placed inside in such a way that when RF is passing through it, it can easily pass, and when it is reflected back, the angle of field is such a way that it is reflected to the port 3, where we have water load or dry load, where we can dump that part. And this circulator is very important for every RF source. It is placed at the start of the RF source amplifier. Then it is also placed if we have a distributed system. We are feeding more than one accelerating structure. Okay. So this circulator isolate your source and it also isolate other accelerating structures if you're feeding more than one structures. And to increase the isolation between the port third, we have a waveguide which absorb all the power. But if we are using higher power in the waveguide assembly, then we use 4-port circulator. RF from port 1 goes to RF port 2, and when it is reflected back, it goes to port 3, and the power which is reflected from port 3 goes to the port 4. Sometime, as you talked about distribution, when we are using 4-port circulator, we have to feed reflected RF part to one of the oscillating structure. I shall discuss this in detail, 4-port circulator in detail tomorrow. Inshallah. Any question?
I have a question.
Please.
So when you have two rectangular waveguide coupled to a circular cavity, you show the TM mode has distorted, right? If you have one arm and instead of two arms.
Let me show where I have shown this. This one.
Yes.
Yeah.
So for two arms, can you like feed from one arm and use the other arm with the plunger? Have you done
No,
this?
no. Here we are not using plunger. Here we are using only RF to the accelerating structure.
I understand. So you feed the accelerated structure from both arms. Can you feed it with one arm?
Yes, we
And
can
the
feed. We
and
can
the-
feed.
And the second arm will be a plunger.
No, there is no need of plunger. Plunger is needed where you have to distribute your RF power. You want to send 10% of RF power to the structure, or 20% or 30%. It is in the waveguide assembly, not with the coupler to the accelerating structure or accelerating port.
But if you have two ports, now you have to take care of polarization, right?
Yeah,
You have, but if you have one port, it's easier to couple. But the
Yeah.
problem with the distortion.
of course. But distortion is there. Then you have to. Then there is this sort of distortion. You have to design in cavity such that it is slightly elliptical, not circular. And when you have both sides coupled from both sides, that you have deformation in the design is mitigated. But here, when you are coupling from both sides, always TM010 mode is excited in the cavity. But the problem can be the phase difference. If you're generally the path length is increased or decreased or can be different, that path length can cause the problem. You have to count the phase length. Here, advantage of this coupling is that when you are coupling RF from one side, there is one window, and higher power coupling causes more heat. But if you split the RF power into two and couple it from two sides, then heating at that RF window is also halved.
Yeah, I have seen for amplifiers, for high power amplifiers, I have seen two arms, four arms coupling also.
Maybe.
And sometimes they do one arm, and the other arms they just use tuner to plunger to
No.
tune the power and couple it.
Amplifier doesn't use coupler tuners. This is the cavity. If you look at this cavity here, you have two coupling ports. Here is tuner. Now, to keep the symmetry here, you have two tuners. Tuner is slightly inserted in or pulled back.
Stops.
So you symmetrically insert it in or pull back. Actually, you are playing with the volume of the cavity, decreasing the volume, increasing the frequency of the cavity, or increasing the volume by pulling back, you are decreasing the frequency of your cavity.
Maybe I can add something. He's asking that if you have a port, a cavity, and to balance, if someone wants to balance, then that plunger that you were talking about can be useful. And in some cases, people still use that plunger thing. But here it is the other thing. They are injecting power from both the ports. So balancing is one thing, injection is the other phenomenon.
Then if you have a single cavity, generally this sort of cavities are subharmonic bunchers in accelerating structure.
And imagine that you have a very huge structure, for example, for 500 megahertz. So designing a plunger which has such a precision is a task. So but inevitably you need something to balance it. So what you do is that you use the other port as a vacuum vacuum port. So in that way, the things are balanced as well.
Any more question? I'm seeing a lot many bright faces, future of Turkey, but they are not participating even in questioning. Why?
Because they already know these things.
That's good.
Yes, you-
That's very good. Okay.
Okay, there's no question. When you do simulation, what software do you use for?
CST, mostly
CST.
CST. HFSS, high frequency simulation structure, CST, Superfish. My main task is designing of accelerating structures.
So use Superfish, huh?
Superfish at very initial stage, and then CST.
Yeah. So 2D simulation.
Yeah, to the Superfish.
It's free software.
Yeah.
For people.
In third world, all softwares are free. You can get pirated versions of all type of softwares, and they do the same job.
Not
What you get, what job is done by the software you purchased for investing million rupees.
Thank you for this great details.